It's a great pleasure to welcome you here tonight for the university's lecture series called Science in the University. It's an opportunity for us here at Western to bring our science and the science of our students and our colleagues to downtown Bellingham, and we're delighted. My name is Jeff Wright. I'm the Dean of the College of Sciences and Technology. This is the first of our series this year, and we're delighted with this exceptional turnout. Thank you all for participating. Our speaker tonight is going to be introduced by one of our senior faculty in the mathematics department in the College of Sciences and Technology, Arpad Benyei. Arpad.
I don't know about being senior, but okay. I wanted to just say thank you to Dean Wright and Chaling, although he's not here, because they were very excited about the idea of bringing Mike to Bellingham, first of all. And thank you, Janet, also for brainstorming about this idea and making it happen. I was asked to say a couple of words about Mike. Well, first of all, Mike started as a circus juggler and a clown for several years before deciding to be a math teacher. And then he decided to go to grad school at Florida State University to get a degree, a PhD in math education. And of course, while he was doing that, he was also in the student circus. He did trapeze, juggling, and slack wire. He then started his math education career at Western in 1999, so that was 13 years ago, 14 years ago. In 2009, so 10 years later, he moved to Norway. He took a position at the National Center for Mathematics Education in Trondheim, as you can see from there. He's working there with teachers, with students and schools around the country to improve the math teaching. And he has over 100 publications on a range of math-related topics. He also runs his own company designing and building math rooms for schools, math furniture, math products, books and games. He writes children's books, poetry, music, performs theater. He loves teaching and getting people excited about math, of course. He's also been a math artist for the past 10 years, over 10 years, presenting artwork around the world. He does 2D and 3D math artwork and animations, most of which is done using people. And this year, actually, he won the top prize at the Bridges Math Art Conference in the largest mathematical art show in the world. Mike Naylor, thank you for being here.
Thanks so much. I wanted to start out, would it be okay if, Bronco, here we are, we're shaking hands. And there's the normal way we might shake hands. And we'd have to shake with both our right hands because our bodies have certain symmetries that we have to think about. If I try to shake with my left hand with his, or my right with his left, pick one. Okay, now we have some problem. We got to break in symmetry with this. It doesn't work out very well. Our bodies force, our bodies have some shapes that force some constraints on how our bodies can go together. What if we had 3 people who met at once and wanted to shake hands? Can you grab 2 people next to you and the 3 of you come up with a way that you can shake hands using 3 people? Okay, so we introduced 3 people, and then we have a whole new range of problems. And I saw some of these had different symmetries. Some had some people were crossed and some people were not crossed. Did anyone get a three-way handshake that was entirely symmetrical? Okay. Here's one way you might try. Maybe I can try this with Millie and Janet. Hold out your right hand, and let's put our fingertips together. Okay, and now let's curl your hand up so that it's closed, and we roll together. And what's kind of nice about this is generalizable. You can do it with as many hands as you can fit around a point, and I've maybe done it with 15 people with that one. But there's one way, and there's many ways that you can do that. So there's a little sample of kind of how fun it is to do math with your body and to think about what can we use our body for with mathematics. There's been lots of artists throughout the ages who have used mathematics to structure their work. Okay, and some artists have really used math very explicitly. Leonardo da Vinci, in his notes, we can see he really paid a lot of attention to mathematics and being able to structure the figures. And so I like to turn that around, and I like to use human shapes to present mathematical ideas, kind of go the other way. If we use human shapes, can we show the mathematics instead of hiding the mathematics in the forms? So here's some of the areas that I draw from, my ideas. And I'm going to show you ideas from each of these areas tonight and how I've represented them with human forms and what we can learn about geometry when we try to express it using body shapes. Polyhedra is where it all started for me. I loved Polyhedra for as long as I can remember. And Polyhedra they're 3D shapes made out of polygons. Poly means many. Hedra means seats. So you can think of polyhedra have many places where you can sit on them. And here's the most popular set here. These are called the platonic solids. Okay, so polyhedra are 3D shapes that are made out of polygons. And here's the platonic solids that were named for Plato, who was a Greek philosopher around 400 BC. These are like the super symmetrical 3D forms. They have identical faces, edges, vertices, and angles. And what's kind of really cool about them is there's exactly 5 of these. There's 3 that are made from triangles, 1 is made from squares, and 1 of them is made from pentagons. And there are no fewer and no greater than that. And that was kind of special to the ancient people. They thought, oh, this must have some kind of mystical significance. And Plato thought that these were the shapes of atoms. This was like the periodic table of elements in ancient times. And do you know what the 4 elements were? Fire, earth, air, and water. Yeah, everything was made out of combinations of those. So this was an early atomic theory that, oh, this is maybe what these atoms look like. And why is there 5? Well, we'll talk about that in a second here. What I'd like to, one thing that I did was I played a lot with polyhedral kaleidoscopes. These are made out of mirrors, and you can put them in certain arrangements. If we make some mirrors with the planes of symmetry in a cube, we can put shapes inside of these triangular mirrors, and they reflect around to make polygons. Like, see that little triangle you see right there? We reflect it in those mirrors, and it makes a whole cube. Or this cube frame right here is made out of just half a cylinder that's reflected over and over to make 48 copies to make this cube right here. And about 10, 15 years ago, I was really fascinated with this, and I put all kinds of shapes in here and play with them in these little mirrored toys. And what I really wanted to do is I really wanted to go inside. I wanted to walk inside one of these. I wanted to be a polyhedron. And so I began playing with computer graphics. What would it look like? I wanted to try to visualize what would this look like if we could go inside of one of these mirrored images. And this was perhaps 10 years later, I finally made the animation that I wanted to with walking inside. But let's take a look on this, on what happens if you can go inside. What you're looking at right now is one human figure. Maybe you can spot her. She's right in the middle, standing upright. That's one figure with 3 mirrors that is making all of these shapes. And something strange happened. This little video, this was in a film festival last year. It has some voiceover there too. You can find it on YouTube or on my homepage if you want to hear the words that go with it. But something really strange happened when I began working with the computer and modeling with human figures. I suddenly realized I really don't need mirrors to make these shapes on the computer. I can make them without mirrors and have multiple people. And then how wonderful it would be, I could have the people touching or holding on to each other, or I could do so much more with them without the mirrors in the way. So this was the start of trying to visualize these things using people. Was really the start of my art project that has really obsessed me for the last 10 years. Here's my first set of renders that I made of the platonic solids using people. And the very first of those that I made was the cube shape that was made out of 4 women. This one just recently, here's another one that I made out of 3 male figures with, you can see, some interesting arm interlocking that we can do. And here's the cube, which stood for Earth. That original cube that I had, I've recently constructed a model for 3D printing, and now I have a 10 centimeter cube sculpture with those. I've also made a male figure with that as well, and they can snap together in interesting ways. And that was in a gallery last year. Here's my latest cube that I made last summer. This is out of 6 figures this time. And this was part of a whole series that I made using the same 6 figures to create all of the platonic solids. So here's the cube, that means Earth. Here's the same 6 figures to make a tetrahedron. Tetrahedron represents fire to the ancient Greeks because this one is very prickly, right? If you touch this one, ow, this one hurts. And this is where we get the word pyramid from. Pyre means fire, means flame. So a pyramid is that flaming, the shape of a fire atom. Here's this one. Here's the octahedron. This was a compact form that could probably mean air. And this is also made out of the same 6 figures. This is the next most complicated dodecahedron. Has 12 pentagonal faces. This one was the oddball out of the platonic solids. And this one represented the universe. There were the 12 houses of heaven, which we now have the 12 zodiac symbols. And so here was the 12-ness of the universe in this shape. And finally, the one with 20 sides is the icosahedron. This one is very rolly, so this one represented water. They have some really nice connections, really nice mathematical properties. Here's a very simple listing of how many faces, how many flat surfaces, how many edges, and how many corners they have. And you can see some very nice properties. The cube and the number of faces on the cube is the same as the number of vertices on the octahedron, and vice versa. The number of edges that those 2 shapes have is identical as well. And we have the same kind of relationship between the dodecahedron and the icosahedron. They have the same number of edges, and the faces and vertice numbers swap. What was very useful to me constructing this was, you'll notice that bottom row right there, the number of edges, each one is a multiple of 6. So I could make all of these using 6 figures where I divide up the edges in a different number of ways. And I started thinking about this by drawing on some polyhedral dice with a marker and saying, how could I arrange people on this one? And once I realized that I could do this, I began cursing myself because I suddenly had the idea, hey, I could make an animation then where one shape morphs into the next one using the same figures. And I became really, really mad at myself because it sounded really hard, and I knew I had to do it now because it was like such a cool idea. So I was a little bit lucky to have some sick leave last year, and I spent about 3 weeks putting together an animation, and it goes through all of these 6 figures. So here's my. Here we can watch now. We'll go from an icosahedron down to a tetrahedron using the same 6 figures. And now we're back to the start again on that one. The figures are arranged in pairs along the x, y, and z axes with 180-degree rotations between them to make all of these except for the tetrahedron. I had a break in symmetry on that one that I didn't know about. And I had to think, which way do I arrange these figures? How do I make them move? And I learned an incredible amount about these polyhedra that I would have never learned if I hadn't been using human figures to do it that have certain symmetries of their own that I'm trying to piece together to make these shapes. So it was a very, very powerful learning experience for me. And I took this animation, I put it looping in a frame so it perpetually loops, and I put that in the show at the Bridges Mathematical Art Conference last year. Last year it was the biggest math art showing in the world ever, and that's I was very lucky, very honored to receive the Best in Show award for that. So that was a real honor to have my colleagues in the field nominate me for that. So that was. Okay, so that launched the project. Next thing would be I'd be interested in was tessellations, tiling patterns. I love these too, fitting shapes together now on a flat surface instead of rolling around. But before we get to there, we should know a little bit about polygons. So I've added this little section in here to show you some things about polygons. Gon means knee. A lot of people think polygon means many sides, but it doesn't. It means many knees. These are shapes that have a lot of knees. And so we're really talking about angles when we're talking about polygons. The most basic of these is the equilateral triangle. One of the top 3 books ever published, you can think probably, okay, there's probably the Bible and the Quran are 2 of them, but in that other top 3 is no, it's not Harry Potter. It's Euclid's Elements. It's a geometry book that was written 2,000 years ago, and people still read it to this day. And the very first thing in the book, after you set up the rules for what you can make in geometry, the very first thing you make, book 1, proposition 1, is you can make an equilateral triangle. So this is like Genesis 1:1 in math world right here. It's the equilateral triangle. When you can think of that, you can think, this shape is the start of all geometry right here. That equilateral triangle. So it's kind of a special shape, that one. That has 60-degree angles. That'll become important for us. Maybe you can see a pattern in the formulas up here as we go along. The square was always a symbol for honesty and justice, and we still say today, yeah, you got a square deal. Get our 3 square meals. That guy's kind of a square. How does that fit? I'm not sure. The pentagon, this is a squirrely figure right here. It doesn't always play nice with other figures. It's kind of mystical and hard to make. This was a symbol of the Pythagoreans, if you've heard of Pythagoras. They were a school that went for hundreds of years. Some people say the Pythagoreans are still amongst us today. Talk to me afterwards if you'd like a membership card. Okay. 6 sides has 120-degree angles. That's very efficient for packing. 7-sided figure has really weird angles, 120 and 4/7. What is up with that? Weird. That doesn't play nice at all. And this one is extremely difficult to make with the rules of classical geometry. In fact, it's so difficult you can't do it. And this really bothered people for a long time, but this shape's pretty special. And so with this collection of shapes now, we can put them together and say, how can I fit these together to make some tilings? These are called tessellation patterns, when we fit the shapes together to cover an infinite surface. Here's one that you probably know pretty well. Squares fit together very nicely. But it's kind of fun to think about the angles in there, and why do they do that? Well, we have 4 90-degree angles, and they fit together to make 360 degrees, which will fit all the way around every point at the corners. We could say, yeah, triangles, we can tessellate with those also. And we can do the same kind of trick and think about why can those tessellate? Well, we have 60-degree angles, and 60-degree angles also fill up nicely to make 360 degrees. So they will tessellate. Hexagons, those have 120-degree angles, and so 3 of those will fit together to make 360 degrees. Also, awesome. What other shapes can we do that with? Well, triangles with their 60 degrees, we can say, 360, we can go backwards now. 360, divide that by the angle and see, 6 of them come together. Squares, we get 4 of them come together. Pentagons, 3 1/3 come together. That doesn't really work. We have a gap left over with pentagons, so we can't use those. Hexagons, yeah, we get 3 of those. Heptagons, no, forget it, 2.8. Octagons, 2.6, 2.57, 2.5. As you complete this list, you get closer and closer to 2 and never get there. In fact, the only ones that you can tessellate with are the triangle, the square, and the hexagon. And so maybe like me, I was a little bit disappointed when I learned that. I thought, there's only 3. Okay. But when mathematicians run out of ideas, you just add some more rules, or you change them a bit, so you open up the playground and make the playground a little bit wider. So maybe if we're dealing with people, we could say, well, I like this shape, I like this Y shape that I made these women to make this hexagon. I could use that Y shape and I could arrange them to make triangles, and now maybe I can see there's some relationship between hexagons and triangles here. I could combine them together and make some rhombuses that fit together, and that almost looks 3D to me. And I thought, yeah, okay, I'll make one of those that's 3D, and that's kind of weird. That's like Cubert, if you remember that game from way back. Or maybe I can try blending the shapes together to make some other nice designs. Or maybe we can say, what if I don't limit myself to just one kind of regular polygon? What if I blend them together? You could say, well, okay, I'm going to start with a square, and then I'm going to arrange my squares around a hexagon, and I'm going to continue the pattern outwards and keep doing the same thing over and over, and I can get a nice tessellating pattern here that uses some multiple shapes. I want to tell you a little something about this picture, because this was a nice surprise to me. When I started making it, I made a ring in the middle of alternating men and women, and then I just followed naturally out the logic of putting the shapes together. And you see those circles further out? We have one that's all men, and then on the bottom, all women, all women. I thought, whoa, why is that? What will happen if I continue moving this pattern out? Will it keep going all men and all women? It looks like that's what it's starting to do at the bottom here. What is the pattern of circles of men? What is the pattern of circles of women? Will I ever come back to a point where it's alternating men and women? And this happens to me all the time when I'm making mathematical art. Not just with people, but any kind of mathematical art. You put some energy into your picture, and it gives you gifts back. It asks questions back to you. You're like, oh, now I got to go something else. I got to go find out now. I don't know. And you feel like you're tapping into this wonderful world, secret fountain of ideas, because you are. If you structure your artwork, if you structure anything after mathematical ideas, math connects to everything. So whatever you're making is automatically connected to all these other ideas, and it's full of surprises just waiting. It's really wonderful. Folks have asked me, what happens with this if you go out? And the answer is, I don't know. I've never tried it. It's been on my list of things. Oh yeah, I have to get around to that and find out. But I realized recently, I don't want to know on this one. This is the one that I kind of want to say, I'm just going to leave this hanging, and I'll be okay with a little mystery in my life on this one, and I'll pursue some other things. So if you want to find out on that one, that would be great, but don't tell me. I want it to be a secret on this one. So this one's called the 6-4-3-4 because that's the arrangement of polygons around any one of the vertices. The 6 is the hexagon, and then there's a square, and then a triangle, and a square. That's a useful designation if we're trying to organize these. We could begin to think, what kind of other shapes can we put together that will fill in? And we have all these angles to work with, and this could be a little bit of a puzzle. You can say, which of these can I put together to make 360 degrees? For example, I might find, 135 plus 135 plus 90, that's 360. What is that? That's octagon, octagon, square. And here they are put together. Octagons. This is a popular pattern for like kitchen tiles. You've probably seen that shape before. Here's another one that works out. 2 hexagons and 2 equilateral triangles work together. That's a 6-3-6-3. Here's one with a dodecagon, a 12-6-4. Here's one, a 12-12-3. I like this one a lot. Here's this there's a single male figure. He looks kind of anguished in this picture. But what makes this work is that element that I have, that piece that I've built to build this, has exactly 12 edges around the outside. And so you can put 4 of them together to make the complete dodecagon. And the triangles are built into his elbow and knee in that figure. There are 8 of these that you can make. I've made all of these using people. And I'd like to give you a little bit of insight into how I design these. It's really a low-tech way that I think about this. I start with a sketch. Here's the tessellation that I want to make. How can I fill this with people? And I generally like it to be as symmetrical as I can and have the people be all the same if I can help it. So I might say, hey, I'll try that Y shape. I've already made some Y figures for other things. Can I have a nice Y shape? And with a Y shape, I could put 3 of them around each hexagon, and that could be pretty cool. And how's that work? And I begin filling in, and then you see all those little gaps in the middle that I can't fill with Y shapes. And I say, that's not going to work. All right, well, that's okay. Let's try, how about this kind of shape, a lowercase y? I could see this to me looks like it could be a person with their legs sticking out. Let's see if this one works with 3 edges. And those could arrange around a hexagon and make like a cool star shape. Oh, this could be nice. I could do something cool with that. Okay, and then I begin filling in, and I say, I got some troubles. They're going to have some overlapping in there. Overlapping some places, not overlapping other places. No, I don't want that shape either. Okay, I'm getting desperate. How about a nice straight line? And I could have 6 people lying around like that. And I could fill in like that, and there's I'm still missing some edges. This one was driving me crazy. This one was, I'm going, oh, what am I going to do with this one? And I thought, well, there's 6 gaps between each of the figures right there. What if I shared an edge? If they reached out like that. Then I could have identical shapes. They'd have to share an edge. And here's the figures that I decided to go with. So I said, let's use a man and a woman, and they can be reaching out towards each other. And that's the shape that I could use, and that. I could use to fill around a hexagon and fill it all in. And so finally, I've got it. I've made a tessellation. And I usually like to finish these. I like to put an edge around them, find out how big they should be, and make a boundary on that. And so that seemed to be the right shape on that one. So there's the 6, 3, 3, 3, 3, and that was one of the harder tessellations to make. And that's kind of what I play with. Okay, fractals, another very rich area. Fractals are structures that are one way to think about them is that they're made out of copies of themselves. It's a little bit weird to think like if I had a glass of water and I accidentally dropped it on the floor and it broke into 100 pieces. And I picked up the piece and it was a little tiny glass of water. Then that was good. I got 99 more of those. You know, it would be a really strange thing to happen in the normal life. But you can do that with fractals. You can do that with geometry. And it is quite nice. They're quite pretty when you do that. I like to introduce the idea with making a fractal tree. If we take a line segment and then follow the rule, I'm going to make 2 line segments half the length off of that line segment, and then I'm going to follow that rule again and again and again. It starts getting more and more complicated, and then you have to do that an infinite number of times, which is a little bit time consuming, but we can use our imagination and just say, okay, I'm going to pretend that goes on forever. And then you can look at any little tiny piece of this and zoom in, and you see it's exactly the same as the whole thing. So they're quite beautiful shapes by themselves, but they have really, really neat mathematical properties as well, because they tap into this world of infinite series, which have some really surprising and elegant mathematics. Here's one of the first fractals that I made. This one is called Family Tree, and it's based on this idea that you've got 2 parents, and each of your parents has 2 parents, and each of them has 2 parents, and you are like part of a fractal tree, like that tree we just had up there. You're maybe the trunk of that tree, and your whole family line is stretching up above you or back in time, and it's a fractal. It's this really cool shape, and it sort of exists in time and in relationships, and I think that's kind of cool. And we can zoom in. I guess in real life you'd have a lot of crossovers later on if you went back in generations, but I think in theory that's a good tree. When I made this figure, it had 2,048 figures. It was the most computationally complex figure I'd done up to that time. I had it rendering on my laptop over the course of several days, and it overheated. The battery swelled in my laptop, and I couldn't use the keyboard for 2 days. I thought I'd destroyed my computer rendering this, but it recovered, so that was nice. Here, we'll use these guys right here to make a fractal. We're going to replace the 3 corners of this with triangles, with the original shape. And now each of these triangles has 3 corner pieces that we could also replace with triangles. And now we replace each man in there with triangles again. And we keep doing this again and again. And we make a very well-known fractal figure that's called the Sierpinski triangle. And this has a lot of really beautiful properties. It's got no area, but it's got infinite edge length in there. This shows up a lot. But what's kind of interesting now, do you see the little guys up there? They're gone, right? We replaced them. They got smaller and smaller. These could just be line segments right here. They've totally vanished. We could have begun with anything. We could have begun with pickup trucks or dinosaurs and gotten the same picture right here. And so if I'm making art that have people in them, I want to be able to see the people. But how do you do that if you're making things that go really small? So one technique that I use is, if I'm going to make some fractals, is I'll try to keep the different sizes in there as we go along. So now I'm going to make that same fractal, but I'm going to make it in a different way. And I'll start with the middle triangle now instead of the outside triangle, and then add 3 triangles around the outside. Okay? Different technique now, and again and again and again. And now we end up with the same figure, but it was made in a different way, and that's kind of cool too, that we can use different rules but come up with the same shapes. And now on this one we can see that we can see the different levels in there, which I like that. Here's one that I made stacking up people in a way that I talked with some circus folks on this too, and they said this could be done. This is the way these people are supporting each other in there. We could make this one for real. So yeah, we have a cheerleader in the room, right? Yeah. Okay. Here's your homework for next time I come visit. I want to see this. Okay. Okay. Okay, here's another one. Here's a nice wiggly figure here with 4 parts that we're going to replace with 4 parts, and do this again and again and again. And we get a very nice curve with some wonderful properties called a Koch curve. And you might see this one, 3 of these curves put together to close a loop, and it looks like a snowflake. So people just call this a fractal snowflake. And I like this shape quite a bit too. Here's a really nice property. That big triangle in the middle right there, if that has area 1, that infinitely wiggly area of the entire thing comes out to have an area of exactly 8/5, which is kind of crazy that it's so nice, perfect number that it has. And yet this figure has an infinite perimeter. That's weird. Like if you began stretching this apart, stretching it out to try to make it into a circle, you just keep stretching and stretching. It is so infinitely wiggly that it's hard to wrap my head around this, even after years of playing with these and thinking about it. They're wonderful shapes. Let's play with this snowflake a little bit. Here's filling it with Sierpinski triangles to get kind of a fun effect. Or maybe we could use this shape and make a tessellation out of it. And look what happens when you tessellate with it. The spaces in between are little mini Koch snowflakes, and they really are. They're the exact same shape, and they're filled in. And you say, oh, look at that. And maybe you can think, oh, that tessellation kind of has the 6-3-6-3 configuration to it. And we can see funny things happening if we superimpose these shapes together. So that's a fun thing to do. Or we could say, well, what if we put the shapes inside and outside? We go right here. And then, wow, you can see lots of kind of neat spirals happening in there as well. So that's fun that sort of the negative space of this is the same as the original space right here. And did you remember they started out being people? Sometimes we do this and sometimes folks come to look at the artwork and they're like interested that it's people, and after a while you just like totally forget that it's people because the math is so cool. It like overrides everything. You know, that's like the coolest part is the math, but sometimes it takes a little encouragement to come and take a look at the math, but that's what really does it best for me. And here's the same idea, trying to preserve that it started with people. So there's that shape. Okay, here's using some fractal algorithms now on the complex plane. And I took that square figure. This is called a Drost effect here, where you use polar coordinates and radially scale the shape going in so you can stack them up again and again and stretch them out. And using various fractal algorithms with a program called the MathMap plugin for GIMP, if that means anything to you. You can do lots of fun stuff with that. And these are all come out of using that same square figure we saw originally. And I don't know, these are kind of weird and cool. I made a series of 5 of these, and I cut it down to 4 to be at one of the Bridges conferences in, I think that was in Hungary in 2010. So there's a kind of a freaky little surrealistic series there using some math. Here's I made this one the same time that Mandelbrot died, and this was shown in 2011. This is a web of people that follows the fractal curves of the Mandelbrot set. And oh, here's an old. This is old. I have a. I thought if you wanted to make a picture that had nothing but jugglers in it, how could you do that? In order to know that they were jugglers, they'd have to be juggling. But what could they be juggling? Could they be juggling beanbags? No, because you want a picture with nothing but jugglers. So they'd have to be juggling other jugglers. But how would you know that those things that they're juggling are jugglers? They'd have to be juggling something too, and the only thing they could juggle would be jugglers. So you're stuck with this infinite number of jugglers going deeper and deeper and deeper. And so I made an animation out of that. It's a little choppy. This is really old. If it's making you dizzy, focus right in the middle. Focus on the little tiny red juggler now, and hold your eyes right in the middle, and you can see it does stay focused on one point if you find the right point in there, and then maybe you won't be as seasick watching this. So that was kind of fun. Like that. The 4th dimension. I had to do that with people because that was just too wonderful. Give you a little tour. We can start with 0 dimensions, and so this woman right here has volunteered to be a 0-dimensional point. And if we decide to take a 0-dimensional point and stretch it in a direction, we can get a line segment. So we're going to stretch that out to get a line segment right there, and that's in 1 dimension. Now we pick another direction, and we're going to stretch that line segment in a different direction, and you can picture that line segment stretching out to become a square, and that's going to be in the 2nd dimension then. We've made a square. Now we pick another direction, and we stretch that square, and we stretch it in a 3rd dimension, and we get a cube. Okay, we take that cube and we pick another direction, and this is where it gets kind of weird, especially if you're stretching at 90-degree angles. But actually, there's no troubles in geometry for putting 90-degree angles, as many as you want together, if you're using other dimensions. But here we get right here, stretching it in a 4th dimension right here. So this is a hypercube, a 4-dimensional hypercube. And all of these shapes, they have some really cool properties. And if you want to entertain yourself sometime, write down vertices, edges, 2D surfaces, 3D volumes, 4D hypervolumes. And you can try to fill this in for starting with a point and then a line segment and then a square and a cube, which you can count. And you can use some logic to try to figure out, well, how are these transforming to get one to the next one. I find it fun every time I do it to think about these things, and you can continue this outwards. It's kind of fun math kicks. Okay, and finally some ideas from topology. Topology is studying relationships between shapes, how things are connected, and they can be independent of what the shapes are. Lots of fun topics in topology. Here's a neat topological shape, Borromean rings, which is named for a part of Italy where these were quite popular door decorations. And these 3 figures are all linked together, but if you remove any one of these figures, the other 2 parts are not linked. They can be separated. And so let's remove a different figure. And so any one pair of these circles right here are not connected to each other, but all three of them together, you can't pull them apart. So this has become a symbol for strength in unity. When we all stand together, we are very strong. And if a part of it breaks, then the whole thing falls apart. So that's a shape that I quite like. Here's another little topological experiment. I met a glass artist in Trondheim who said, let's do something mathy and glassy. And he said, okay, let's try putting a figure into glass. And we tried several things, and we finally went for this, this person right here. And I designed these cross-section pieces right here. And then he printed that out on glass and cut them all together and put them together, and maybe you can see it makes a person in the glass in 3D, which is pretty cool. So we have some plans for other designs that we might make something on a very large scale with people walking down sidewalks and walking dogs and things like that. We'll see what comes out of that collaboration. That was a fun thing to do. Here's one of my earlier images, which has become one that's become the symbol for my project. It is a pentagram inscribed in a pentagon. Some people say that and say, hey, isn't that like a witchcraft symbol? And then I have to get all indignant and say, no, you're thinking of the pentacle, which is a pentagram, five-pointed star, a pentagram inscribed in a circle. This is the pentagon. This is a pentagram in a pentagon, which is the symbol of the Pythagoreans. This is a very important geometric mathematical symbol right here. So don't be careful with our symbols. This is awesome one right there, and in the circle is not nearly as awesome as this one. So you know, it's also a connected K5 graph. It's if you take 5 points and you make all the connections you can between all the points, you get this shape as well. So there's a little graph theory in there as well. This shape I've earlier this year I prepared this file for 3D printing, and I had to redo the whole file to do that. But I made some jewelry now, so I have it in a stainless steel necklace now for that. And you can order in time for Christmas, so yeah, ask me about that, yeah. But that's fun. I have a lot of other plans for jewelry that's based on many of these models that you've seen here, including the platonic solids that I also want to make some large-scale sculpture with. So it's coming for next year. Okay, here's just playing around with some figures, and here's some female figures that with a pentagram in a different arrangement, and I've played with lots of different symbols, but it's still, the original one is still my favorite, the pentagram. And now using that same pentagram and some of these effects that I showed you earlier, I made a spiral out of that, which has some really nice golden ratio things going in, and that turned into a large print on some thick acrylic that was in the Bridges conference in Baltimore earlier this year. So this brings us to the end of the artwork that I wanted to show you. I hope today you got to learn some neat ideas about math and kind of see what goes into a creative process when we're trying to use mathematics to make us better artists and to use artwork to show some good mathematical ideas. Thank you all very much for coming out to see my stuff. I appreciate it, and if you want to stick around afterwards and talk to me about stuff, I like stuff too. So, okay, thank you very much.